This is the video demonstration for EE533's Lab 7, which is on NetFPGA integration and on DETERLab. So first we swap in our experiment. So here is the NS file, the network simulator file, which we use to create our experiments topology, which it consists of my 5 nodes. Four nodes are connected to a single node, which is acting as a router, and it has actually a NetFPGA is acting as a router in this case, and we can make it simulate as a reference NIC or a reference router according to our desires. So this is a visualization how the nodes look like. So here we can see for each and every link for the server and the router, they have their unique IP addresses, as you can see here. So for instance, for N0 we have this 10.1.0.3, and on the NetFPGA the ports IP stays as 10.1.0.2. Similarly it goes for other nodes. So when we head over to the details, so this is uh, the most important information which we look for: the physical LAN/link mapping. Here we will find our nodes' respective MAC addresses and their IP addresses mapped to it. Why I'm saying this is important, because this using this information we would configure our router and our nodes on the DETERLab. So the things we want to see here is the last octet of the MAC represents the port of our NetFPGA, and our NetFPGA has four 1 gigabit Ethernet ports. So let's say, for instance, this is the last octet is 01. So this is for my NFC1 port, and corresponds to this IP address. Same goes for the NFC3, NFC0, and NFC02. बोलो.
हाँ ठीक है, हो गया बस इसका इसका और इसमें कुछ है नहीं बताना. अब सीधा जाओ अपना उसके.
Now we want to test the ping functionality for our NetFPGA. So the first step is we load our reference router design, reference NIC design to our NetFPGA. And first we try to initially, if you look over here, we try to initially ping N1, but we are, for some reason we aren't. So we figure out that we need to mention the complete name of this node. So how it goes, like, yes. So it should be the name of your node, followed by the project experiment name, followed by, this should be common for everyone. So you see 533 is at DETERLab.net, and as you can see, the ping is fully functional. Now we go ahead and test the TCP traffic on each of our nodes. So before doing that, we need to execute uh, these commands. So what these basically commands are doing is, these are actually used to change the value of the kernel parameter in the Linux OS. The command sets the value of the maximum receive socket buffer size to whatever you're mentioning. So here actually we're mentioning this like 2 million bytes for, like, so all protocols. So let's head over and how this works. See, we need to actually same interaction. We need to make one node as server and one node as client, and we're going to run the iperf command. And to run the iperf, we need to again give the complete path. This is how it looks like. So server port number we're mentioning 3001. The second, again the iperf command, making it acting as a client. mentioning the server's name followed by the port number. So by this, we can actually analyze how much throughput we are getting. In the NS file, we have mentioned our link bandwidth is 1000 megabits per second. So we are getting around 943 megabits per second here.
Done it.
So in the last TCP traffic experiment, we were testing it on reference NIC. So now it's turn for the reference outer design. So we download the reference outer bit file onto our NetFPGA, and we again run the same commands, making node 1 act as a server, node node 0 as a client. The server is in listening mode, and we can see the throughput is very similar in both of the reference designs, NIC versus router. Okay, so now we're gonna run the UDP test on our nodes. So the main motive for this is we're gonna make use of a UDP test script, and the main motive of this test is since NetFPGA has four 1 gigabit ports, and so we want to see whether it can achieve the 4 gigabits per second speed, and even though if it gets saturated. So we have tried a similar experiment where data is flowing from all the nodes up and down. So let me describe you the script and how it works. So we have run a for loop, like we have four nodes. So here the same command SSH, my node's name, making one node acting as a server, and UDP mode, and the port is 3000, and this ampersand depicts that we are putting this instruction uh, in background. Yeah, and since one node is up and running as a server, rest of them should be acting as clients. So same SSH, the node's name, client mode, UDP mode, port, the bandwidth 940 megabits per second, the packet size 112 bytes. This is the frequency of the report which we want, so like 5 seconds, and the length of the experiment, like 30 seconds. And when it's done, we need to kill all the processes. So that's how we do it, kill all MLab hyper. So let's head over. So we are running our UDP test bash script. So making every node acting as a server and client, and data is going up and down. So here soon we would be able to see the throughput of each node. So we can see. So we actually ran this experiment multiple times, and we were able to achieve the consistent value of 1.02 gigabits per second. This experiment is gonna go like for 30 seconds because we mentioned it. So now we'll be loading a bit file for our mini ideas design. So I've download. So you can see our design was successfully downloaded, and now we are actually going to check the matches registers value. So dot slash IDS matches registers, we're going to print it, and it shows 8. So this means our design is actually working. If it were not, it would have showed dead beef actually. So now we're going to go ahead and reset this. So after resetting, we are again printing the register value, and it says 0. So this means our design works. And one more thing I would like to mention is that this IDS script, this is not available on our DETERLab server, so we had to actually copy it from our Fedora uh, to the DETERLab through FTP, so that we could successfully read our hardware registers. Okay, now to actually when you're building your logic analyzer, we need to configure hardware and software registers. So what are hardware and software registers? So hardware registers are actually read only, and if you want to manipulate our hardware registers, we need to do it so through the software registers. So the only way to manipulate our hardware registers is through the software registers, and we do it, and this happens via the PCIe interface. So so first, how many? So you head over to the ideas.p file, and there are a few lines where you can actually mention the hardware registers and software registers. So in this dot hardware reg, you add whatever your register names is. Same goes for your software registers. And when you head over in the generic reg section, you increment the number of software and hardware registers as many as you added. So in here we actually just had 3 software registers and 1 hardware register. Now the next step is you head over to the ideas.xml, which could be found in your project folders include folder. In here you need to add all your software and hardware registers in this format. So like let's say for this instance, this for the software register, so its name followed by just a brief description and the type of register, which is a generic 32-bit software register. Same goes for this add in, and that matches. Now when you generate your bit file, you would want to know where these hardware registers addresses have been mapped by the FPGA. So you know this, you find it out uh, from the reg defines .h file. So you can find this in the directory in your project folder. Head over to the lib folder, then C, and you can find this red underscore defines.h. Just scroll over and you would find the addresses. So here for our in the IDS file, the matches register. This is the address. So for CMDN. This is our register. This is the address, and we face a problem that sometimes this res defines underscore labsex.h doesn't really get auto generated. So in this case you should actually delete this file, because anyways this file is going to be auto generated, and afterwards go to the synth directory, execute a make clean and followed by a make, and after a successful bit file generation you should see this file with updated timestamp, and then you can head over and check the addresses for your registers. Okay, so since now we know the addresses for our registers, we actually went ahead and created a script which could automate the reading and writing of the software and hardware registers. So this is a portion where we have mentioned the addresses of our hardware and software registers. So you might just want to focus on the line 15 where just we're writing, and then line 28 we're reading, making use of the addresses, and line 32. So this is just how you want to make use of the addresses mentioned in the res defines collab6.h file. Uh, okay, so actually there is actually a bug in the design. So what it does is, so first we look at the fall through small v4 design which is found. This is a library defined design of the NetFPGA's reference order design. So in here we can see the input of the fall through small v4, where the small v4 is instantiated, the data in and data out ports are connected. But if you talk about the empty flag goes through a series of combinational logic. So here we have the empty next, followed by this empty flag again. So there is actually a one clock delay this empty signal is facing. So but since it's a library defined file, we need to make changes in our ideas design. So in here we just so this is the diff. We have compared the old ideas versus the fixed ideas design. So in here we have just gone ahead. So instead of directly, you know, connecting the data input and the control with signals, we have gone ahead and made new signals which introduce a one clock intentional delay, which is desirable to us. And there's one more thing. So this is the old ideas.b. So in here, if you see in my detect 7b module, its data input is ideas.v is directly feeding it the input data to it. So in control and in data. So this actually changes things. So because we don't have the delay and how why is ideas.v feeding the data directly to ideas to detect 7b. So to fix that, actually this fall through small FIFO should be the one inputting the data to my direct 7b module. So this is the second change. So to reiterate, the fall through FIFO has a small FIFO inside such that the input and the output from the small FIFO is directly connected through my fall through small FIFO. But when the empty signal comes out of the small FIFO, it is subjected to one clock delay. And when it comes out the fall through, so this makes the data and empty flag out of sync. So this is the reason we did this. So we could solve this. We solved it by adding a one clock delay to my design. And second one being ideas.v's input is directly connected through my fall through FIFO. But that is fine. But it shouldn't be connected to my data 7b. So to fix this, we had to give the output signal of my fall through FIFO to my data 7b module. Okay, so now we're gonna test whether in our working mini ideas design which we downloaded to our native VGA, whether we are getting the traffic in both the modes TCP and IDP, UDP. So to test it out, first we need to figure out which Ethernet port that specific node is connected to. So to do this, we would be running sbin. So root sbin if config. So you can see here, so say it says node 0 is connected to ETH5. We will repeat this for all the nodes. So node 1 goes by ETH4, node 2 is at ETH5, node 3 is at ETH4. There we have it. Then we will run the TCP dump command. So again, sudo, you have to access the complete path. So root user sbin TCP dump. You have to mention the Ethernet port number, link number. So for this it was ETH5, so that's why we written ETH5. So I'm gonna skip a bit and repeat the same command on different nodes but with the respective Ethernet port number. So here we will run the same UDP test which we ran previously on the reference router design, but now here this would be our mini ideas design. So as we know that so in here, so in the UDP test bash script, it doesn't have we haven't mentioned anything about the pattern, so we have to be the one giving out the pattern. And as we know in the message, if it doesn't fit the datagram, padding happens and it is from 0 to 9. So in here, let's see, I'm going to give a pattern called FFFFF, and let's see if the matches register increments or not. So I bash the initialize script, and this is the message I am giving. Again, all the nodes and all the servers act out as clients and servers. So as I can see, the matches count doesn't increment. Why? Because of the nature of my the message I gave, because it doesn't have padding. And please note that the value of this matches register is initially set to 0, uh, and this is actually part of our experiment, and it is totally intentional. So, so in here, in this UDP test, we have given the 1 to 7 pattern, and in here every datagram would match. So basically we have set our malicious code same as padding, therefore all the datagrams will be dropped, and at the end you would see the total number of, yeah, the total number of datagrams generated by the 4 nodes are roughly like 2.4 million and are equal to the value of the matches, that is in hex. So in this type of experiment, we are giving a pattern again, but there is also a message involved. So let's make the nodes on listening. So this is what our message looks like, and in here I put random as my pattern. So let's see what would be my matches count. So we can see the matches count is 1, where in my message and where my pattern was random, and in this message it found x 58 hex. So now I have given the pattern generate, so let's see what would be the matches count. says 58. So we're repeating the same experiment but now in the TCP mode. So first we would give pattern generate and see if my matches register increments. This is my message, and here is a TCP script and my pattern. You can see the matches count turns out to have 3D. Again repeat the experiment but now with another pattern, namely ABCDEFG. So since that message doesn't have any word matching to a pattern, so it gives out 0 as the matches count. Thank you.